on last this class, if I happens to share my screen, we started actually discussing a very important concept, and that was called as degrees of freedom. All right. And I told you that specifically a degrees of freedom is nothing but the independent input parameters uh, which which determines or which can produce the uh, position or the orientation, or which can detect or dictate the position and orientation of a manipulator or a robot for that matter, will be considered as a degree of freedom. That's basically a definition. Now, for in general, for any mechanical structure, we will always have a degree of freedom. Since, as I said, the robotics also deals with a mechanical, heavily dependent on mechanical engineering, and a part is definitely mechanical in nature. So definitely it will also have a degree of freedom for that matter. And in that aspect, I told you some of the small little discussion as such, that if I consider a point in a 2D space, it will require 2 degrees of freedom, because we need 2 inputs to discuss or to describe that particular point. But if I consider the same point in a 3D plane, then we would require x, y, z as 3 coordinates to describe that particular point. So in our context, we will call the previous scenario as 2 degrees of freedom and the next scenario as a 3 degrees of freedom, because there are 3 inputs. So similarly, if there is 4 inputs that you are considering, then we have 4 degrees of freedom, 5 degrees of freedom, and 6 degrees of freedom, and even more. But ideally, when you only consider a planar movement or a planar manipulator, mostly it is dealt with the position of the object or the position of the manipulator with respect to a given structure or a mechanical structure. And in that way, we discussed that we had already discussed that 3 degrees of freedom is a usually it is referred to as the planar manipulators degrees of freedom. Whereas when we are looking at position plus orientation, especially for the rigid body dynamics, then we usually consider as a 6 degrees of freedom system. But to be honest with you, most of the cases that we are going to discuss today, and in fact in our syllabus, whatever we have, is primarily a planar manipulator, because it's relatively simpler to work out in a class environment to discuss and decide on the the details about a manipulator. Considering that orientation, the 6 degrees of freedom spatial manipulators are absolutely fine for the industrial point of view. So if you are leading towards more and more rigorous discussion on robotics, definitely 6 degrees of freedom based system and analysis of it will be helpful. I'll tell you that you will get that clarification after a certain period. So this is what we had discussed. In fact, 2 other things that we had discussed. One was called as a redundant planar manipulator or redundant manipulator, and an under actuated manipulator, where the under actuated stands for if any planar manipulator or a spatial manipulator is working less than the degree of freedom that it has, then we are calling it an under actuated system or an under actuated manipulator, be it a planar or a spatial. If it is planar, like if it is less than 3, we will call it as a under actuated planar manipulator, whereas if it is greater than 3, then we are looking at as a redundant planar manipulator. So just remember in this way that whenever we are looking at greater than the maximum degree of freedom for planar or spatial, we are looking at a redundant system, whereas when it is less than the degree of freedom but it's still working, then we are looking at an under actuated system. So that's basically what we are discussing. So today's discussion, we are going to discuss a very interesting topic, as I was telling you, and that is basically how do I calculate the degree of freedom for any mechanical structure, okay, or any given mechanics. If you have, how do I calculate the degrees of freedom? So let's see that one by one that what exactly is meant by it. So before that, jumping into the DOF, let us take a very simple example, okay, just to understand the concept just to understand this a little carefully. So suppose I have a system of this nature, because now we are all aware of the joints and movements and everything, so it's pretty clear. Suppose I have a specific joint, or we have a link, rather we have a link which stands like something like this. All right, now this is my X This is my y. Now, in order to describe this particular object, what we can understand that we can actually have an x and y, okay, that will decide on both the direction x and y, wherever the position of A or the position of B is, so that it will be decided by it. Or if it, what it can do is like it can move towards some direction over here, or it can move to some direction over here maybe. So this is another alternative, like either in x direction or y direction or both the direction, or even what it can do is basically it can also rotate about any of the axes. That is also possibility. All right. So what I meant by this is that that link that we are looking at, okay, it can have at max 3 coordinates in which, or 3 I would say motion that we are associated with if I'm considering this 2-dimensional space. So basically we are looking at the 3 coordinate system, 3 coordinate system, okay, or 3 coordinated movement if you call it. Suppose I will mark it as x a, y a, and theta a. Okay, so we need a x direction movement, we need the y direction movement, and maybe a theta direction at some point. That is enough to discuss about this particular link, right? So if this is the case, we are looking at a scenario where it is 3 degrees of freedom. Basically, you can see that this is a 3 degrees of freedom that we are looking at. All right. Now, if you add another link over here, now see what happens. Okay. Now, suppose I have another link somewhere over here. Okay, and I mark it as C and D. And suppose, important word, they are unconnected. They are unconnected. All right. So there is no connection between them. They are standalone links. Now, you might say, what is the purpose of it? It's basically it's a hypothetical scenario. No manipulator or no mechanical body can stay like this, but it is suppose the hypothetical scenario where 2 links exist, something like this. So what we can do that for this CD link, there also we might have maybe like XC, YC, and theta C as another 3 degrees of freedom for the brown colored link. All right, but you can just very nicely you can observe one thing. Okay, I'll do a small little change and see what happens. Okay, so let me just remove this link over here. Okay, and I'll put the link, the same link, somewhere over here. Got the idea what I'm meaning? Initially it was unconnected links. Okay, they were just standalone links, and they were having 3 degrees of freedom. Okay, or you can say even the mobility in that context, and they were lying somewhere. But now suppose there is a revolute joint that is joining this. So revolute joint which connects the 2 links together. So this is my L1. Let me mark this as L2. So now L1 and L2 are marked. L1 and L2 are marked with respect to a revolute joint. Now what happens, you see that when I'm adding a joint, understand this carefully, when I'm adding a joint, basically we require less number of inputs, okay, to describe this particular arrangement. Why? Because you can observe that if I consider this as X, suppose this is my XA, okay, let me take another color, X or maybe red, XA, all right, so this is my XA. This at this point rather we will sorry I'll just redraw it a little bit so that the is, yeah, so this is my structure. So this is my position of A, so XA. Corresponding to here we would always have a YA. All right, now suppose there is an angle of theta which is connected somewhere over here, that is the initially this angle of presence, okay, and there is another angle which is theta B. Okay, now you can observe that in this particular arrangement, if I'm having a revolute joint in between 2 links, we are reducing the number of inputs from 6 to 4. We only need XA, YA, theta A and theta B, because they are connected system, if you call it connected system. So the conclusion is that the revolute joint makes some kind of a constrained, okay, we call it this word as a constraint. Any joint, if it is a prismatic joint or a revolute joint, whether it is a rotating joint, whatever it is, it will create a system which will have a constrained motion. All right, so this word is very important, constrained motion. So if it is a free system where there is a link, only standalone link, whatever the degree of freedom it will have, for a connected system, definitely it will be less. Am I clear with this analogy? If you have any doubt, please tell me. We are discussing how to calculate degrees of freedom. Okay. I started off with some standalone system where the degrees of freedom we can understand how it should be. But when we connect the two systems, ideally we are observing the less number of inputs are actually determining the position of this particular manipulator or the arrangement, not the manipulator. Let us consider it to be the arrangement. And we are concluding that whenever there is a joint, we would definitely have a reduced sorry, I got disconnected maybe. All right, so let me am I sharing the screen maybe by any chance? No.
No, sir.
No, sir. I'll just reshare it. I somehow got disconnected maybe. Yeah. So I was here that what exactly is meant by constrained motion. Now let us continue our discussion on this. Some of the important conclusion that we have drawn. So the first thing that we can write after the discussion that we have, that if a revolute, please you can make a note of this also. If a revolute or a pin joint, sometimes they are called as the pin joint. Okay. Now basically what does that mean? Pin joint. It is a joint that helps. I'll just write it down. It is a mechanical structure, but for our understanding, it is also needed. A joint that helps in turning, okay, or rotation, something like this. So that is basically a pin joint. So a revolute or a pin joint permits a single DOF, okay, because it's a only rotation that it is allowing to happen between the link that it connects. Clear from the idea what I discussed. A revolute joint that is only helping is to turn. So basically it only requires theta A basically. So it will require it is allowing a single DOF between the links. What is the conclusion from this? And that is very, very important. The conclusion that we can draw, that introduction, please make a note of this, introduction of one pair of, okay, one pair, or rather instead of pair, I'll just add one point over here, one lower pair, I'll put it in capital, okay, one lower pair, or, because this is the crux of our discussion, lower pair. So introduction of one lower pair or binary joints. Binary joints, we'll see what exactly is binary joints, cuts, okay, 2 degrees of freedom. So this is the conclusion that I'm drawing, that if I'm adding up a binary joint, now what is a binary joint? Let's see. We'll go back here. Binary joint is like this. See this particular joint over here. So this particular joint has 2 connections, one here, one here. So this particular revolute joint will be considered as a binary joint. So whenever a joint is connecting 2 links, we will consider that as a binary joint. So if you consider here, and that in our term, it is called as one lower pair. So this term is important. Lower pair. It is a term coined from the mechanical engineering, not from electronics by any means. This is called lower pair. Okay, and that is actually reducing the DOF by 2 degrees of freedom. Done. Second conclusion that we are drawing is a higher pair joint. Now this is again a new term. A higher pair joints. What are these higher pair joints? Suppose we have a gear mechanism. Okay, we'll see with example. Don't worry, just for the time being you write, or maybe a roller. Okay, if you consider this kind of a movement, or maybe like one surface is touching the other. Suppose this is one surface and suppose this is another surface. So this point contact, if you have something like this, these are all called as higher pair joints. Okay, in mechanical system. So higher pair joints, all right, permits 2 degrees of freedom, okay, between the joint or between the link it connects. All right, so this is basically the conclusion. Now based on, so like here, lower pair has 2 degrees of freedom, reduction in 2 degrees of freedom. Similarly, a higher pair will always have 1 DOF reduction, or one higher pair will reduce the overall DOF by 1. All right, so if I put everything together, so the degree of freedom can be calculated as, this is the crux, the degree of freedom or DOF is given by a specific equation, and that is called as 3, please make a note, into n minus 1 minus 2L minus H. Now what are these elements? We have already defined that. N here, this one, okay, we are discussing this particular equation. N here, where N equals to number of links. So for any mechanical structure, N equals to how many number of links which are present. With example, we are going to discuss that. Don't worry, for the time being, just make a note of it. L is basically the lower joint, number of lower joints. Okay, the lower joints we have just discussed over here. So basically we are discussing some of this revolute joint or a binary joint where a single joint is connecting 2 links. Okay, so that is basically L. So we have to estimate how many number of lower pair are there, okay, or any binary joints are there. And finally, H stands for the number of higher pairs, okay, or number of pairs having 2 degrees of freedom for that matter. All right, so this is basically what the idea is. This particular equation that you are referring to, okay, this is called as by a name of a scientist, because he is the one who coined this, and this is called as the Kutzback criterion. Okay, so this is a famous Kutzback criteria to determine the DOF for any rigid body with respect to mechanical system. All right, 3 into n minus 1. Now you can observe that this 3, why we have discussed, why we do have this 3, because this equation that you are referring to, this is actually for the planar manipulator. This is for the planar manipulator. That's why it is a 3. The same equation extends to the spatial manipulator as well. Okay. Now the spatial manipulator would look something like this, DOF. So if I write spatial, so as we know, the spatial manipulator will always have 6 degrees of freedom. So the DOF equation would look something like 6 of n minus 1, okay, minus, see, this is where it becomes a little difficult or different, 5p1 minus 4p2 minus 3p3 minus 2p4 minus p. All right, now you might say, what exactly are these? First of all, 6nn is the same thing that we have discussed. P1, which is over here, it determines number of pairs having 1 degree of freedom. Okay? Number of pairs having 1 degrees of freedom. P2 similarly in the following the same rate, pairs having 2 degrees of freedom. Okay, these are all about the links we are talking about. P3 similarly will have 3 degrees of freedom, like that, so on and so forth up to 5. So total degree, because 6 is the maximum degree for a spatial manipulator. So whatever is less than that, 6 can't be the maximum because of the constraint that is imposed by the links. So definitely the maximum, the constraint that it might have is 5 degrees of freedom. So that's why P4 and P5 is the maximum times what it can live up to. But as I said, the equation and the calculation over here will not be considered as most of the cases, because we are mostly going to discuss on the planar manipulators. So that's why please keep a mind of this particular equation. 3n minus 1 into minus 12 minus 8. All right. So this is basically Kutzback criteria to determine the degrees of freedom for any mechanical structure. For the derivation of this also, you can refer to some of the books maybe, but they have not directly derived it at any point. But at least in the course material that I'm going to upload, there you might see some of the derivation, how this equation comes into picture. But again, as I said, it is not at all required. So if you are specifically interested, you can look into it. Otherwise, you can omit that particular discussion. So this is what the equation 3 into n minus 1 minus 12 minus 8. See the beauty, like after this with the example you will find. So this is first of the criteria. The second criteria that we are going to discuss, same leading from the same discussion, is called as Grublers criteria. Grublers criteria, because this is a criteria which is derived from the Kutzback criteria. So when the mechanism, please make a note, when the mechanism has only lower pair, okay, no higher pair, only lower pair, and the overall mobility, okay, of the mechanism is unity. Okay, if that is the case, then we are looking at the Grublers criteria for both planar and the planar manipulator, as well as for the spatial manipulator. By this, what I mean is that based on this, we can write that if what is mean by only lower pair, that means h should be 0 in the equation that we just now have written, 3 into n minus 1 minus 12 minus h. So this h would be 0, no higher pair, and we can also see and also say that DOF will always be 1. All right, so this is basically what the stringent requirement for a Grublers criteria is. Okay, because this is mobility of the mechanism is unity always. So if this specific case is there, we will call that as a Grublers criteria. So in that case, what will happen? You can just check the equation 3 into n minus 1 minus 12 minus h. This is equal to the 1. Okay. Now h is equal to 0. So what we can say, 3n minus 3 minus 2l. Okay, this is 0 is equal to 1, or 3n minus 2l minus 4, and that is equal to 0. Exactly this equation that you are referring to is called as the planar manipulator or Grublers planar manipulator equation. All right. Similarly, you can also derive it for the spatial manipulators in the same way, because in that case also you have the higher pairs which will not be present. Okay, only the lower pair will only be present. So that can also be derived in the same way, which I'm not doing as of now, but in the course page you can get the final expression would look something like 6n minus 5p1 minus 7 equal to 0. So this will be the, you can just substitute over there, P2 to P5 all will be 0 because they are all higher pairs. Only the lower pairs will be present. So that's why P1 will be present. So this is called as Grublers spatial manipulator. Okay, spatial manipulator. Grublers criteria. Okay, so this is the crux of it. Now, what is the conclusion finally we have drawn? After that, we'll go to numericals. The conclusion is that if this also is like a mechanical understanding or mechanical engineering understanding, that if DOF is equal to 0, then the mechanism, okay, the mechanism, whatever be it, can be classified as a structure. Okay, it is a structure if it is equal to 0. If the calculated DOF is equal to -1, okay, or less, negative in that way. So this basically forms an indeterminate structure. This is called as, this concludes it is an indeterminate structure. All this is coming from mechanical engineering, so don't exactly ask me like what is the definition of an indeterminate structure, but that is a condition if I want to conclude out of a mechanism. And in all probability, if DOF is greater than 0, okay, that is if it is 1 or anything else, the mechanism, the conclusion is the mechanism can be driven, okay, like it's a drivable mechanism. It can work, it can move, okay, it has a mobility. In that also, for example, if if I consider DOF greater than 1, okay, if this is the equation that I'm getting, or equal to 1, for example. So suppose instead of greater than, let me just put an equal. Okay, suppose your calculated value is DOF equal to 1. So this means, the meaning is only one input is needed for mobility. All right, or a motion, you can say for motion. So whatever be the given mechanical structure or the mechanism that we are discussing, if it needs to move, only one input is enough. So that is the significance of finding the degrees of freedom for that particular mechanism. All right, if it is DOF equal to 2, it means 2 inputs are needed to move that mobility. So hence you have to arrange for the 2 inputs somewhere down the line. All right, so that is basically the beauty of finding the DOF with respect to Kutzback criterion. Now let's take the example. Any doubt till this point? Anyone? Will go to the numerical. I think it will be more clearer to everyone. Yeah, please.
Sir, so my doubt is like, is there actually any difference between mobility and DOF? Like,
No. It doesn't have any difference. Basically, you will find that degrees of freedom is a more colloquial and a more preferred word compared to a mobility. But I have checked in many books, they use both degrees of freedom and mobility as a single definition. So that's why I keep on telling this mobility, because for us as an engineer, like if you consider us as an electronics engineer, it's easier for us to understand that something is moving, something is going to move. All right. So in that way, I feel it is more convenient for us, or at least for me, if I relate the degrees of freedom to something in terms of mobility of the mechanism. So that's why I'm using both. There is no difference amongst both the two terms. They're same.
yes, sir. And another doubt is like, just like, could you just scroll up?
Scroll up.
Yes.
That
diagram which I've drawn, yeah. So like, so for that, let's just assume that instead of revolute joint, like if we consider a twisted joint, so will it? Yeah. So would that still be considered as a constraint system?
Absolutely. Why? Because you can observe that twisted joint, be whatever be the direction of motion it has, ideally it is a rotary joint. It's basically a rotary joint, right? It's a movement is rotational in nature. Rotation means there must be some kind of an angle that is associated with it. If you consider this instead of revolute joint a twisted joint, motion might be different, but ideally the input will be a theta. It's an angle. Rotation, right?
So for that matter, like if you assume any kind of a rotary joint, be it a twisted, revolute, or even cylindrical, so it would constrain the given manipulator.
Absolutely. The point is whenever we are using any link, that's what I'm telling you. Any link, it could have been a prismatic joint also, like a linear joint where the movement is linear. That would have been the same. Whenever you are using a linear joint or a rotary joint, whatever it is, it will have a constraint on top of the overall movement. Understand? So it will restrain, it will lessen the total effectivity of the system or a material or the mechanism that we are handling. That's the basic conclusion. All right, we'll see some of this numerical so that a few more doubts are getting clear. So first of all, we'll conclude that we are going to specifically focus on this planar manipulators equation on Kutzback criteria. We are not going to discuss on the spatial manipulator part, but it is just for your reference that it can also be derived for the same. Now let's take a very nice example so that you are able to understand why it is working and how it is working. Okay, take your pen and paper because we are going to do it together. So I would request all of you to keep a paper handy. So suppose I have a structure. Let's take this as a first example. I have a structure something like this. I'll start with the easiest and then I'll go a little bit tougher. So suppose this is my structure there. Okay, now for the very first time since I'm doing it, I'll mark this as link 1. Okay, I'll not draw it for the next time. This is the only first time I'm doing it. So the nomenclature wise, this is my link 3 and link will be described as hash. Okay, I'll just use this as a symbol for link. Okay, and this is my link 4. So I'll have, if it is hash 2, if it is hash 1, hash 3, it means it is a link depicting a link. Okay, now and this dotted dot that you are looking at, this is basically a joint that we are talking about, and mostly this is a rotary joint that we are considering. Okay, so if suppose this is a structure that we are looking at and we have the equation as we know, DOF is equal to 3 into n minus 1 minus 2l minus h. So we'll first write it down. Okay, now let us try to find the parameters out of it. So as we have discussed, n is nothing but the number of links. Straight away you can observe that the number of links over here is 4. So we get a 4. No problem. Now we come to L. What was L? L was the binary joints. As I said, binary joints are basically a joint which will connect two such links. So if you observe that here, I will mark it as 1 binary. I'll make a circle here. 1 binary. I'll circle here. Because you can see why it is binary, because link 1 and link 2 are connected by this joint. So it's a binary joint. So it's 1. Link 2 and link 3 are connected by this joint. So it's 1 binary. 3 and 4 is connected by this. So this is a 1 binary. And this is also connected by 1. So this is another boundary. So maybe you can use this kind of a circle or something like that so that you are able to figure out, because you will soon find that the figure will get a little complex. So it might be a little difficult to get hold of if we are not drawing them properly. So what we can do is that easily we can find out that there are 4 such binary joints which are present. And we are observing here that h is equal to 0. Why h is equal to 0? Because you can observe that neither in this mechanism, no such joint exists where there is a roller or a gear mechanism or another surface that is touching on top of it. Nothing is there. All right, so there is no higher order pair, hence h is equal to 0. All right, clear with this very simple example, because if you understand this simple example, the other things also you will understand. All the other numerical you will understand. 4 links are present, 4 binary joints are present, and there is no higher order pair because there is no such roller or a gear mechanism or a touching of a surface or a point contact. Nothing is there. So hence h is equal to 0. I need a very clear understanding on this, whether you are able to figure out whether it is clear to everyone. Can I hear from some of you at least?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir. This is clear, right? Simple, very good. So if this is the case, I'll substitute simply in this equation. So 3 into 4 minus 1 minus 2 into 4. So this means 3 into 3 minus 8, which is 9 minus 8, and this is equal to 1. Just now I had a conclusion drawn. If it is greater than 0, the mechanism can be driven. So basically this system, this mechanism, the conclusion, if I suppose this is your question and the final answer, final question is conclude on your finding. So the conclusion over here is, so the mechanism would require one input, because its DOF is 1, it will require one input for a constrained motion. This word constraint is very, very important. Don't miss out. Okay, so this is a very simple example that indicates how the Kutzback criteria can be used for a mechanism. Now let's, with this idea, let us just try to get a little bit more on it. Okay, so let's take something like a structure of this nature. I'll again put a very simple way. Suppose this is my end effector. Okay, this is a specific structure of it, and they are being used in mechanics for that matter. So suppose this is a structure given to you. Now we have to find what is DOF. Okay, what is DOF? Using the formula 3 of n minus 1 minus 2l minus 8. All right. So very clearly we can observe that first we have to note down all the links. So you can observe simply, we can write something like this: 1, 2. Hopefully you are also doing with me so that you don't wait for me to give you the solution. Please do it all together. Okay. Now you can observe I was about to give this as a link, but this is not a link. This is basically the end effector which is connected over here. This is not, this part that I'm just trying to use the hash over here is not a link. Okay, please understand this carefully. This is not the part of the structure or the DOF. This is just an end effector which is connected on top of the structure. So we are not going to consider this as a link by any means. Okay, be careful in this. This is the structure. We are calculating the degree of freedom of the structure itself. Okay, not the end effector. So this is basically the structure. Now n is done. So basically simply we can observe n is basically 5. Same way, just like the previous one, we can observe that this is my one binary joint. This is my one binary joint. This is my one binary joint. This is another binary joint, and this is another binary joint. So basically n is equal to 5, L equals to 5. Do we have any H value, higher order value? If we have, can anyone tell me if it is any value, any?
Yes, sir. That's
any gear or any roller system, something like that is there or not? The answer is no. I have not given you any example up till now. This point, okay, the one that you are looking at, again, it's confusing. It is just an end effector, and it depends on how this mechanical structure is moving. So rolling joint means, suppose I just change the diagram a little bit so that I think all of you might be having a similar kind of doubt. So let me just redraw it a little bit. Okay.
Sir, I have a doubt.
Sure, go ahead.
Sir, let's assume that end effector, it's a rotor, it's a rotary equipment. So about that come under roller and gear and stuff like that.
Something like this. Something like this. The diagram I just now had changed. Suppose I have an end effector which has a surface, and the surface is going through some kind of a rolling structure. You can see over here. Just assume, hypothetically, you imagine that this is a rolling structure, that it is a very unstable diagram in that way. But anyway, if suppose it is there, if it was present, H would have been 1. Okay, but since it is not there, we will consider H is equal to 0. I'll give you specific examples of H value is there or not. I'll tell you that. All right, and even we'll find that L is not that simple to calculate at times. We'll see that in the next problem. So simply you can substitute over here and you will get degrees of freedom. Am I made myself clear? Though I don't know who asked the question. Am I clear with this H? Why it is H equal to 0? Okay. So degree of freedom for this is calculated as 2. So basically the conclusion is that if I have 2 inputs which are present, this particular mechanism will be drivable. All right. This is a simple example. Now let's see, we increase our complexity a little bit. Okay, so we have a structure now like this. You can also draw it with me. like this. Okay. Now we have a structure of this nature. I'll explain everything, don't worry. Just draw the structure first. Okay, simple. And this is shaded. Okay, this is always shaded for a reason. Now suppose this is a mechanical structure that we have, or a mechanism we have, and we want to find out that what is the degree of freedom for the same, using the same equation, Cn minus 1 minus 2L minus H. So this is the equation. The first things first, remember, because this is a little different question to that of what we have solved so far. First, what is the rule is to find all the links, because we have to find out what is N. So you can observe that although, please make a note of this, although this particular end, and this particular end are lying in different directions or in different places, ideally they are all grounded. So as per the rule, we would consider that these links are this particular ground, actually this grounded part is basically one link which is considered to be 1. Please make a note of it. This is a fixed link because this is ground, right? Ground means the manipulator or the body is fixed to that. So that also needs to be considered as a fixed link. And the fixed link is a one link. You can see if this would have been somewhere here, that also would be considered as one. All right. So all the ground in that way, you can remember in that way, all the ground should be considered as one fixed link. So all have been given a nomenclature of #1, right? Same way, if you consider this one, now the rest of the things are pretty simple. #2, #3. I'll tell you what about this. #4, #5, #6. All right. So 1, 2, 3, 4, 5, 6, and I think I am missing anything. Anyone? 5. No, I don't think I'm missing anything. Just give me 1 minute. 1, 2, 3, 7. Yeah, it's fine. Eh? Yeah, it's fine. Fine then. But I think I missed any one link.
Sir, I think the one that's next to #3.
Next to this one, you are saying?
Yeah, that one, sir.
I'll tell you that I think I made a space of the thing, or it's fine.
Sir, the center leg should have one more joint, sir.
No. I'll tell you. It's fine. This is fine. So 6 is the normal conventional joint that you are looking at, a link you are looking at. But what about this shaded part? Now this is another new thing that comes up. This shaded portion, okay, this part, this kind of an arrangement that you are looking at, it is called as ternary link. Please make a note. It is called as ternary link, and the nomenclature or the diagrammatic representation is something of this nature. Okay, what is a ternary link? Basically a link that has 3 nodes. Okay, a link which is consisting of 3 nodes. You can see, observe that this particular link, this whole structure has 3 links that holds this structure. So they are called as ternary link. Now what do you mean by ternary link? Whenever we are calculating a degrees of freedom for any ternary link, we would consider that as a single entity. That means we would consider this as #7 only, not this, not this, not this. All together this triangular shaded region is one link. Am I understandable to everyone? This is called as ternary link. Ternary link means that first of all, this is the identification of a ternary link, and a ternary link is all together, it should be considered as one link. So although we have something over here or we have here, we won't name or nomenclature based any naming we won't give. Clear? So basically my N is coming as 7. 6 was already there, and this is the one link, so 7 is N. Clear? Now let's see the L. Can anyone give me quickly what is the value of L that you might calculate? How many binary joints do we have? how many binary joints we have? Binary joints, how do you calculate? You just compare with two links, like one, let me just take another color, green maybe I'll take, 1 and 2. So this is one binary link, okay, somewhere here. 2 and 3, so this is a binary link. 3 and 7, see, 3 and 7, this is a binary link. Although it looks like there are 3 links, but basically you have to read it this way, 3 and 7, how it is connected? Through this link. 3 and 4, okay, 3 and 4, or rather not 3 and 4, 4 and 7, how it is connected? It is connected via this, so this is a binary link. 6 and 7, how it is connected? It is connected via this link, so it's a one binary link. 5 and 6 is connected by this is a binary link, and 5 and 1 is again connected by a binary link, so this is a binary link. Am I clear with this? I'll go slowly again. Each and every link, as I said, as per our rule, all the 2 links should be connected by a single link, that is called as a binary link. Here you can observe that 1 and 1, the ground, the fixed one. Let me check what happened. The first and the second one is connected by this link. 2 and 3 is connected by this link. 3 and 7, okay, 7 means this whole structure is a one link connected by one binary link. The same structure is connected by 4 by this one binary link. Same structure with 6, one binary link. 6 and 7, 6 and 5 is connected by binary link. 5 and 1 is connected by another binary link. So total number of and even 4 and 1. So this should be another binary link here. So total number of binary links 1, 2, 3, 4, 5, 6, 7, 8. So we have total 8 number of links which are present. All right. And similarly, just like the previous discussion, H is equal to 0 because we don't have any higher order links. So you can just substitute over here 7 minus 1 minus 2 into 8. So that means 2 into 6 minus 16. All right. So sorry, 7. Yeah,
18.
I think it should 3 only. Yeah. So it should be 18 minus 16. So it's 2. Again, the conclusion is that this particular mechanism can be movable with 2 inputs if you are submitting, like if you are giving an input of 2. Okay, so this is another set of different structure that you are looking at. Let's take a different question. I don't know how much time is left. Already is 9. I don't have. I have a lot of numericals in fact given. Let's take one H value. Let's do that, and if time permits, we'll come and do a question on the other side on the next class maybe. Let's take an example, very simple example. Okay, this is a 4th example. The other questions are also there in the course page, so you can try it out. So the 4th one, suppose there is a diagram of this nature, just to understand that value of H. All right, that particular case if you look into. So let's have the diagram maybe like this. You have a welded rotor like this. Okay, now this is a rotor. This is connected via a link like this. So this is one such kind of a connection, but this is a complete, this circular thing is welded. Okay, so let me just shade this part. So it means that it's welded. That means the whole structure is one. That's the meaning of it. And there is a structure which connects something like this. And we have a base on this particular base. The link is rotating like this, and this is rotating of this nature. Okay, so this is the mechanism. Suppose this is the mechanism which we have, and we have to find out a degree of freedom for the same. So in the same way, just like we have done previously, see over here, these are the fixed links. So basically this fixed link will be considered as #1, and this is also #1. Second link is this particular link which is rotating like this. So maybe we can say this as a generic 1, 2. And as I said, the whole structure is 1. So basically we will consider this as 3. If the circle that you're looking at over here was told as not welded, then we could have said that this is a separate link itself. But since it's welded, it's a complete structure itself. So 1, 2, 3. So my n is equal to 3. Now you can observe over here how many links do we how many binary joints we have. Okay, so you can observe very clearly one binary joint that it has is this one, because 1 and 3 is getting connected here, and 1 and 2 is connected somewhere over here. So simply we can say L equals to 2. Am I clear with this? I think all of you are clear. And now you can observe that at this particular point that I'm pointing out right now, there is actually a point contact. Okay. So as I was telling you earlier, if there is a point contact, if there is a gear mechanism, if there is a rolling mechanism, something, because all those things are having a point contact somewhere. So if this is the case, so H in this case will be 1. All right, so this is a higher order pair that we are having. So 3 is the link. So we substitute in the same equation that we have, minus 2L minus H. So 3 into 3 minus 1 minus 2 into 2 minus 1. Okay, minus 1. So it's 3 into 2 minus 4 minus 1. So 6 minus 4 minus 1. So it's actually 1. So the whole structure, although it looks so complex in nature, the degrees of freedom is only 1 that we can calculate out of this. All right, so hopefully this is clear. I can't extend the class beyond this point because it's already almost 9. So what I'll do is I'll just give you one short, small little task. Okay, let's see how much you can do it. You can solve it and you can give it to me. Okay, you can share it in my chat or in the in my personally. You can send me over in chat. I'll give you the structure. Okay, so let's see with the concept, whatever you have learned, I hopefully you will be able to solve it. So this is the structure. Please draw it. Okay, so this one we had already done. Okay, now let's make it a little complex. So this is shaded. Hopefully all of you would know that why it is shaded and what it means. Then we have a connection like this, and we have a connection of this nature. Okay, and this is again connected something of this nature, and this is also connected by same nature, and this is again the same structure. Suppose this is the structure given to you, mechanism given to you. The question is to find out what is the degrees of freedom. Okay, this is sample number 1. Sample 1, and the second sample that I'm giving you is also like this. I'll try to draw it over here. Okay. Because diagrammatic representation. This is 1. Okay. Please bear with me for a little bit long so that this. And we have like this, and we have a structure here, we have a structure here, but these are shaded, this is shaded. Okay, and this is the ground that it belongs to. Let's see how much you can able to figure out this. Explain that once again. Another shade, and to make things worse, I'll make this also a shade. So I'll just mark this as a different color maybe. So this is basically the ground plane or the fixed link that we have. So given these two samples, okay, kindly finish your work, okay, and submit it to me. Take a photo and send it to me in chat. Okay, let's see whether you are able to figure out. Also, if possible, you can write one line on the conclusion that you can draw out of this two segment. All right, so let us finish off on that note. Hopefully this has been a learning experience for all of you, and let me start sharing as well as stop recording.